All right, last class I introduced you to Project 4. Over the weekend I finished it up, wrote a bunch of different implementations, some that I expect you to get, others that I don't expect you to get, but if you beat me, that'd be great, so please do that. All right, so minimum overlap. For this project, we're trying to find the minimum overlap of sets that still cover all points. I think the best way to understand that is with an example. So let's say we have numerous group projects for our class that need to be presented at the end of the semester. Your professor, aka me, must grade every student at least once, but I'm lazy and I don't want to assess more than one grade per student. Due to the nature of the project, students are members of multiple projects, but only once present once. How can we minimize the number of times a student has been presented? Naturally, everyone in a group has to present, aka there's no partial group presentations. To recap, here are the requirements, so it'll be a little more straightforward. Each student is issued an ID starting at 0. We do not care about their names. Each group consists of a set of numbers. Keep in mind that a group cannot have the student in there more than once, aka you can't be in attendance of a group or twice. You know, the group is not PJ, Matt, Jonah, Matt, and Jonah again. That doesn't make any sense.
Well, what? People with the same name.
Nope. Well, we're only by ID number, so we don't care about you.
What if there was a mistake? Two students who give the same ID?
Yeah.
A query consists of a group of numbers. A student may be in there more than once. Okay, let's say I need to grade students 0, 3, and 4, but I need to get another grade for 4, so I might query for 3, 4, and 4 again. So I may ask for more than one, to grade a student more than once. But a student can only be a member of a group once. Okay? All right. When a group presents, all students are graded. I'm not going to grade only part of them. I grade the entire group. Your function must return the minimum number of grades your professor has to assess. So that's it. Just the total number of grades, that's the minimum. So obviously, if I say I need to grade 1, 3, 4, and 4, the minimum you could return is 4 because I need to grade at least 4 times. But the number will probably be higher. If it is not possible to satisfy the query, return uint max or -1 if they're actually the same value, whichever you prefer. All right. Does the problem make sense now? For those of you online, go to the previous lecture. I think I explained it fairly well that time as well. All right, real quickly, your files. Each file in the data directory contains a group of sets which represents a group that may present. So let's go ahead and look over here. If I do an ls on data, notice I have different sets. Actually, I have some timing as well. That's fine. But let's look at our simple vim data simple.set. So this group is 0, 2, and 4. Next group is 0, 2, 3. This group has just 1. Fourth group is 0, 2, 6. Fifth group is 1, 4, 3. And the last group is 5, 6. So those are the groups I can present. The main.cpp is general purpose test program for running your test cases on your code. It produces timings as well. I have already written this for you. You are welcome. The HPP is a header file for you to compute the minimum overlap. The CPP is your source code. Right now they have nothing in it because that is your job. The simple is going to have the data set that's provided below that we're going to look at a little bit more. Small 30 is the small for evaluating basic timings. Medium 30 is a little bigger. You should strive to master that one. Large 30 provides basically bigger than large 50 is the largest. Set group files. Each set is contained in one line and is spaced a limited list of numbers. Each group represents a student ID. For example, 025. Oh, yeah, we just went through this for now. Let me give you some examples. If we want to find the minimum of the query, I need to grade student 0, 2, and 6. The answer is 5 because we have to choose 0, 2, 5 as well as 5 and 6, and that would be the minimum. Because if we chose 2, 3, 6, then that would have been a 6 because I would have had to assess 6 grades. But by choosing this one down here, I only had to address 5. You see how that was done? Minimum of 1 is 1 because we just choose group 1. And minimum of 1, 2, 2, 3. Notice I said I need to grade 2 twice. I lost one of that student's other's grades, silly me. Is 7 if we choose those groups right there. Notice that for some of these, there's multiple different groups that you can choose from. Because, for example, it could have been 0, 2, 3 here, but it could also have been 0, 2, 5. And would still give you 7. Your function, I don't care about what the groups actually are. I just need the number at the end. That's all I'm looking for. Here's your interface. We're going to pass the set file, and I'm only going to pass this once. That's why it's a constructor. And then I'm going to call find minimum overlap multiple times. Keep that in mind. So you can do all your pre-processing you want ahead of time, and then afterwards do a find minimum overlap will be called multiple times. This is your hint, because I'm not going to be grading your pre-processing timing that much. You could spend a long time in here, and I'm okay with that, as long as it doesn't take more than like a couple minutes or something. You're okay. So I'm really looking at the timing for find minimum overlap. That's what we're looking to optimize here. This program is using, we're going to use recursive backtracking to solve this. You may have another idea for a different algorithm, but the point of this project is for y'all to learn recursive backtracking. So your algorithm needs to look like something that's down here that I've given in the box. And this is very similar to what I presented last week. There's only a couple minor changes. I don't remember what they are, but we're going to go over it. I'm going to pass, well, your function should have find minimum overlap. You'll have so far. Notice I haven't given you the type. Your input, again, haven't given you the type. And then Boolean print about whether you want to print something or not. Minimum starts at max. By the way, you don't have to have this here. I'm just suggesting it. This could be somewhere else. Each set S in the set file, your result is going to be your input, subtract S. Because, for example, when you begin, so far is going to be empty, and your query may be 1, 2, 2, 3. And that would be represented by input. So input might be 1, 2, 2, 3. First off, you take result, which is input minus S, and then if the result has 0 members, that means you've actually found something. Go ahead and update the minimum size. Otherwise, add S, remember that's your set, to so far, and then call find minimum overlap, pass again so far, the result that you have you've computed so far, and then print again. And then you're going to return your other minimum, and then update minimum if you need to. Afterwards, you need to remove the set from so far, and then try adding the next set.
So that's all we have to do, is that right there. We have to figure out how to do it.
Yeah, you have, your algorithm needs to be set up like this. Really, the key thing is there needs to be this recursive call for evaluating the next set. Now, this is recursive backtracking. The key to making efficient algorithms here is minimizing the number of recursive calls. When can you stop trying to recurse? Maybe you can go ahead and jump out. When can you return early from this? When can you stop calling yourself over and over again? Maybe there's some pre-processing you can think of ahead of time that can tell you when you don't need to look any further. Notice that in this code, here's your big hint, is I never checked to see if we're already past the minimum that we've computed so far. For past the minimum, do we need to keep recursing? No. So that's a big jump right there. There are other things in here as well that you can do. There's actually a lot of things you can do. I didn't get to all of them. But your job is to try and find a good number of them, implement them, maybe use the data structures to help store or pre-process some information to help you trim all the recursive calls that are being performed. General algorithm makes sense? Everyone good? All right. You can't change the public interface, but you may add any private data, methods, or anything you want. You must have at least, obviously you're going to need at least have one additional method for this recursive call. Keep in mind the above is pseudocode. I never defined what so far is. You may define it to whatever you want it to be. You could make it a character for all. If you could get that to work, fine. Or you can make it, a vector of sets of B trees. That's perfectly fine as well. Make it whatever you want. I'm not limiting you. Notice that data stored in private sections should not depend on a particular call to find overlap, but only the set group file. Right. Other data should be declared locally and passed as parameters. Pass by reference is faster than pass by value. For anything bigger than a single integer, so consider using that. Keep in mind that const stuff does give some performance improvement, but not much. AKA, if const is driving you nuts, just delete it. You may create as many helper classes as you want. Make them separate, perfectly fine. The public interfaces of those are up to you as well. Make sure they're designed well so when I read them it makes sense. You'll probably need something, a class or a struct to represent set or group, or you can use something from the STL. Either one is perfectly fine. All right, some example runs. One thing I did not tell you about is inside Project 4 there is a bin directory where I have already given you the binary of some of my code. We have M overlap worst. I expect all of y'all to do a lot better than that one right there. M overlap 60 just has one or two very minor changes that greatly improve performance. That'll give you about 60, just FYI. I have M overlap 70. I think that should really be an 80. I just didn't want to rewrite everything to reflect that. So that one will probably give down to 80. And then I have my best that I've come up with so far. And that would probably be more towards 120 than actually 100. So I'm not expecting you to match me, but hopefully you can get something in between and I'll grade accordingly. This is just to give you an idea of what the performance, how your performance is, the performance of your algorithm so far.
Or is this just the grade for the performance side?
I'm only grading performance.
Oh, you are?
Yeah, this is pure performance. Of course, accuracy as well. Because right now, with your default code, your performance is amazing because your function instantly returns the wrong answer. So obviously, you need to be correct.
Which would you rather have, the right answer or to be fast?
Okay, you want the right answer. Let me make sure this is clear. If you get the right answer, I will at least give you a 30. How about that? 30%. Yeah.
I don't know.
Yeah. But if you are wrong, it's a 0. I might be able to assign some points for creativity when I inspect your code, but you need to be accurate first. If you follow the recursive backtracking algorithm correctly, you're going to get the right answer here. It's just then learning what to trim. Now, if you overly trim and I inspect your code, that's okay. I'm really making sure you pass the default test cases that I've already given you. Make sure those pass. You have 4 programs already to show you what the answer should be. So possible runs, let me go ahead and make this a lot bigger. So notice I run min overlap worst, passing in the simple set, saying yes to print everything, and then here are my parameters, my queries. Notice that my queries are in quotes. Now, even on the simple test, the worst is still pretty fast, as you can tell. Found minimum of 6 in essentially 0 seconds, 4 and 0, 6 and 0. Now, all of this is actually, this printout stuff is already written for you. Let me go back, I didn't talk about that. Main.cpp. I have provided this function. I didn't really comment it, sorry. But this is essentially going to, you compile main, and it's going to parse, no, it doesn't parse, I'm sorry. It's going to, where we go? You pass it, there we go, pass it the file, argv1. Notice that up here, program, argv1 is simple.data. I pass that to your constructor, you parse it, make sure you get your parsing done right. Then next is the yes or no. That is simply taking care of another function. And then the rest of these parameters are the queries. So for each additional query, I create it. and then I print it just to show you what it is, and then I'm going to call find minimum overlap, passing the query the cover for you, and the cover in this program is currently a vector of ints, and then the print, and then I get the clock, and then I print it out afterwards. And I'm actually going to do that a lot, and I'm going to store the timings and then sort the timings afterwards so you can see what the timings look like from 0 all the way up to max. So for this one, not too much timing. Let's go for the second one. Small 60 on small 30, yes, passing in those values. As you can see, we're starting to get some timing information. I didn't run worst on this because it takes forever. I think after a minute, I just stopped the program and didn't want to look at it anymore. But yeah, information written to type data/timings. In the make file, you can do make plot, and that will actually give you your plotting information. Large 30 on 0.70. Again, we're starting to get take a lot longer. Notice that it takes about 8 seconds for the full graph, or for the full evaluation, and then writes the timings. All right. This is helpful? Somewhat helpful, hopefully. All right. Let me show you now the make file for this one is unfortunately messy. Make all compiles it. You're probably, let's put in the debug flag in there for you, git add make file. Push that for you so we don't you always have the debug in there, or we'll not have an internet connection. Okay, there it goes. Make run is just going to run that simple test case that we showed in class for you. If I do make run right now, it's actually going to compile everything. Found a minimum of 1,041 elements in 0 seconds. Obviously that's wrong. You need to go and fix that. You can also do make small 30, which actually will do the same thing, but use a little bit larger test. If you look in the make file, you have small 30, medium 30, large 30, and large 50 to represent different levels of inputs. Large 50 is going to be the largest data set I will test against your code. So if you're able to get reasonable answers, you're able to get the answers in a reasonable time on large 30, you're good. Or large 50, sorry, large 50, you're good. Now, you can run small dash timings, which is going to get a lot of timing information. Now, this is where it starts to get a little ugly. Same thing with medium timings, a little ugly too. Large 30 timings, again, and large 50 timings as well. Warning, unless your code is good, large 50 timings will probably be a while. Notice I gave timings, so after you have timings, you can do make a plot, and that'll generate the plot for you. Obviously, the plot right now is something really small because we're not really getting any timing information. Oh, got a little up there. When you have code in there, the make plot, you do first make small 30 to actually run everything, and then make plot will then plot what just happened. Okay? All right. Memory management, I will be looking at your memory management. Go ahead and run Valgrind, although it's more important for this project that you have accuracy and performance. In STL, you may use anything from the STL. I did not see anything where they solved this problem in the STL, so feel free to use anything from it. Don't use Boost. I'm not going to incorporate that in your test. Use anything from STL. This is due December 2nd. Any questions?